Okay, so today we're diving into something pretty cool. You sent over this plan for a computer science course. It's called CF2. And going through it, I gotta say, it's kind of like peeking into the inner workings of how software really works.
Yeah, it is. I mean, the
But
first thing that jumps out is how well structured this course is.
yeah.
It's not just throwing a bunch of random concepts at you. It's clearly designed to build your understanding in a really methodical way.
And you mentioned wanting to get up to speed on this stuff like quickly, but without sacrificing depth and looking at this plan, it seems perfect for that. It's about hitting those core concepts, but also getting hands-on with the actual tools that pros use.
Exactly. It's that balance of theory and practice. Sometimes you get these courses that are so theoretical they feel disconnected from the real world, but this one seems to bridge that gap really well.
Yeah, it's like they're giving you the express lane to understanding this stuff without skipping any crucial steps. So our mission here for our listeners is to go beyond just what is covered. We want to really dig into why these data structures and algorithms are so important. Like, how do they fit into the bigger picture of computer science and software development?
Right. We're going to unpack the core ideas, but also try to show how they connect to the stuff you actually do when you're building software.
All right, so let's start with the structure of the course itself. It seems pretty consistent. Lectures on Mondays and Wednesdays, recitations on Wednesdays, and homework due every Friday. That kind of regular rhythm seems like it'd be really helpful for learning, right?
Definitely. Having that predictability, it plays into how our brains learn best. You get exposed to an idea, then you have time to process it, maybe discuss it with others in those recitations, then really solidify your understanding through the homework, all before the next chunk of information comes along.
And the grading, too. Half your grade is from the homework, then 25% each for exams and a project. That's a pretty big emphasis on the homework, right?
For sure. It really suggests that active problem solving is where the real learning happens. They're not just testing you on memorization, it's about applying those concepts.
So it looks like the course starts in January with a break for MLK Day, another break for spring break at the end of March, and wraps up in early May. Pretty standard schedule. But the weekly topics, some of these names, man, they just sound cool. Like they really grab your attention.
Oh, absolutely. Week 1 and 2 start with a general overview and getting familiar with the tech stack. Got to make sure everyone's on the same page, right? And then week 3, ease in ABB and complexity. Now, what's interesting here is that the first data structure they introduce isn't a classic one. It's axis-aligned bounding boxes.
And they jump right into complexity analysis there too. I like how they're not shying away from the tougher stuff. But yeah, ABBs, those are mostly used in game development, right? For collision detection.
Yeah, exactly. So think about it. You've got all these objects moving around in a game world. If you had to check every single object against every other object to see if they're colliding, it'd be incredibly slow.
Right, especially if you've got a lot of objects.
AEBBs basically give each object a simplified rectangular box around it. And to check for potential collisions, you just see if those boxes overlap. Now, it's not a perfect check, right?
Yeah.
Something could be touching the box without actually being inside it.
Sure, it's an approximation.
But it's so much faster than doing detailed checks for every object. It's like a quick, rough filter to rule out obvious non-collisions. And if the boxes do overlap, then you can do more precise checks.
So it's about trading a little bit of accuracy for a huge gain in speed.
Exactly. And that kind of trade-off is something you see all the time in computer science. You're always trying to find the most efficient way to do things.
Gotcha. Okay, week 4 pointers, linked lists. The notes mention that JavaScript doesn't really have direct memory access, so how do pointers even work in this context?
That's a great question. And it highlights a really important distinction between how different programming languages handle memory. So even though JavaScript doesn't give you that low-level control over memory addresses like C or C++E, the concept of a reference is still super important.
So even though they might not be called pointers explicitly in JavaScript, the idea is still there.
Precisely. In JavaScript, when you have an object or an array, you're not directly manipulating the data itself. You're working with references to that data.
Kind of like having a friend who knows where another friend lives. You don't need their address directly, you just know how to reach them through that first friend.
Perfect analogy. And in JavaScript, these references are how objects and lists are connected and how you navigate through them. It's fundamental to how data is structured and manipulated.
Okay, that makes a lot of sense. Now, week 5 brings us recursion binary search tree. They actually define recursion as recursion and C recursion. In the notes, classic programmer humor. But seriously, how does the idea of a function calling itself connect with these binary search trees?
Well, the thing about trees, and especially binary search trees, is that they have this inherently recursive structure. Think of it like this. Every node in a tree can be considered the root of its own smaller tree. So any task you might want to do on a tree, like searching for a specific value or adding a new one, can often be broken down into the same task performed on these smaller subtrees.
So it's like a divide and conquer strategy.
Exactly. And recursion is perfect for this kind of problem. The function basically says, okay, I'm going to check if the value I'm looking for is at this node. If not, I'm going to call myself again on the left subtree or the right subtree, depending on whether the value should be smaller or larger. It elegantly reflects the structure of the tree itself.
It's like that recursive folder structure you sometimes get on your computer. You open a folder and there's another folder inside and another and so on.
Exactly. And recursion allows you to navigate through those nested structures very cleanly and efficiently.
Week 7 covers stacks, queues, Huffman coding. I've heard of Huffman coding. It has to do with compression, right?
Right on. It's a lossless data compression technique, meaning you can compress the data and then perfectly reconstruct it without losing any information.
So how does that work?
The basic idea is that you assign shorter codes to symbols that appear more frequently in the data and longer codes to those that appear less often.
Kind of like shorthand or using abbreviations for common words.
Exactly. And the way you build these efficient codes is where priority queues and binary trees come in. The priority queue helps you efficiently find the least frequent symbols to combine, and then the binary tree represents the code structure itself, where each pass from the root to a leaf node corresponds to a unique code for a symbol.
And this is used in like image compression and stuff, right?
All over the place. Image files, audio files, video files, data transmission over the internet. Huffman coding is a fundamental technique for making data more compact.
Wow, so this seemingly abstract concept has some really concrete applications. Okay, weeks 8 and 9 dive into graphs, DFS, BFS, finite state machines. Graphs just seem like such a fundamental way to represent relationships between things.
They are. You can use graphs to model pretty much anything, where there are connections or relationships, social networks, transportation systems, computer networks, the flow of logic in a program, even the relationships between objects in a 3D scene.
And DFS and BFS, those are ways to traverse or search through those graphs, right?
Right. Depth-first search, DFS, is like exploring a maze by going as far down one path as you can before backtracking. It's often used when you need to visit every node in the graph and you don't necessarily care about the shortest path.
And BFS is breadth-first search?
Yep. BFS explores all the neighbors of a node before moving on to their neighbors. It's good for finding the shortest path between two nodes, especially in unweighted graphs.
So it's like the difference between exploring every nook and cranny of a single room in a maze before moving to the next room versus checking all the rooms connected to your starting point first.
Perfect analogy. And then there are finite state machines, or FSMs. These are a special kind of graph used to model systems that can be in a limited number of states and can transition between those states based on specific inputs or events.
Like a traffic light. It can be red, yellow, or green, and it changes based on timers or sensors.
Exactly. FSMs are used everywhere in computer science, from game AI to controlling hardware devices to designing user interfaces.
Weeks 11 and 12 focus on applications of data structures and algorithms. They mention things like collision detection, which we already touched on, Voronoi diagrams, half-edge data structures, and tessellations. Sounds pretty heavy.
It is, but it's also where you really see how these seemingly abstract concepts get used to solve real-world problems. Voronoi diagrams, for example, are used in everything from figuring out the optimal location for a new store to modeling the growth of crystals.
What about half-edge data structures and tessellations? What are those used for?
Half-edge structures are a way to efficiently represent the relationships between edges, faces, and vertices in 3D models. They're super important for computer graphics, animation, and 3D printing. Tessellations are about dividing a surface into smaller geometric shapes. They're used in computer graphics for creating detailed 3D models, and also in fields like architecture and art.
Okay, and then the final weeks are dedicated to the course project. They've got a proposal, execution, and delivery phase, plus something called fun topics, which are driven by student interest. I love that they're leaving room for students to explore what they're passionate about.
Me too. It's a great way to keep things engaging and to encourage students to dive deeper into the topics that really grab their attention.
They mentioned that the tests are in person. On paper, no computers allowed. That feels pretty old school.
It does, but there's a real value to that.
Yeah.
It forces you to really understand the concepts and to be able to think through problems logically without relying on the crutch of a compiler or debugger. Those are essential skills for any programmer.
And they expect the projects to be pretty impressive, especially for larger groups.
Yeah, the idea is that as you get more people working together, you should be able to accomplish something more ambitious. It's a good lesson in teamwork and collaboration.
Okay, so we've covered the course structure. Now let's zoom in on those practical technical skills. They make it very clear that this course is about moving beyond just theoretical exercises and into the world of real-world tools.
Because that's where the rubber meets the road, right? Data structures and algorithms are the building blocks of software, but you need the right tools to actually build that software.
One of the first tools they highlight is the CLI, the command line interface. It's about navigating folders, managing files, and doing things with text commands instead of clicking around in a graphical interface.
Right.
Why is the CLI still so important?
Well, for one, it's super efficient. Once you get comfortable with it, you can often do things much faster with the CLI than you can with the mouse. Plus, it gives you a lot more control and flexibility. You can automate tasks by writing scripts, access system functionalities that might not be exposed in a GUI, and work on remote servers in a way that's just not feasible with a graphical interface.
Okay, so it's about power and efficiency. Then they mention Git for version control, and specifically using the GitHub interface. Why is version control such a big deal in software development?
Because it's absolutely essential for managing how code changes over time. Think about it. You're working on a project, making changes, adding features, fixing bugs. Without version control, it would be a nightmare to keep track of all those changes, to go back to previous versions if you need to, or to collaborate with others without stepping on each other's toes.
So it's like having a time machine for your code.
Exactly. And Git has become the industry standard for version control. Platforms like GitHub make it super easy to collaborate, share your code, and contribute to open source projects.
And they recommend brushing up on JavaScript and learning TypeScript. Why those two in particular?
Well, JavaScript is pretty much unavoidable these days. It runs in web browsers, on servers, and mobile apps. It's incredibly versatile. And TypeScript builds on top of JavaScript by adding static typing. This might sound technical, but it basically means you can define the types of data your code is working with, which helps catch errors early on and makes your code more reliable.
So it's about adding some extra safety nets to make your code more robust.
Exactly. And then they mentioned NPM, the Node Package Manager, which is all about bringing in external libraries and tools so you don't have to write everything from scratch.
And that ties into the package.json file, right?
Right. That file basically keeps track of all those external dependencies, so anyone who wants to work on your project can easily set up the same environment.
And they also talk about Jest, which is for unit testing. Why is testing such a big deal?
Because it's all about making sure your code actually works as intended. Unit testing involves writing small, focused tests that check individual parts of your code to ensure they're behaving correctly.
So it's like double-checking your work as you go instead of waiting until the end to see if everything falls apart.
Exactly. It's a fundamental part of professional software development, and it can save you a ton of headaches in the long run.
All right, so we've got the course structure and the tools down. Now let's dive into the heart of it all, data structures and algorithms. The notes define them as organized ways to store data and step-by-step procedures for manipulating that data. Sounds pretty fundamental.
Absolutely fundamental. Data structures and algorithms are like the underlying building blocks of all software, even something as simple as representing a spaceship in a game. You need to choose the right way to store its position, its velocity, its health, and so on. Those are your data structures. And then you need to define how it moves, how it shoots, how it interacts with other objects. Those are your algorithms.
So data structures are about how you organize the information, and algorithms are about how you process and manipulate that information.
Perfect. And they go hand in hand. The choice of data structure often influences the efficiency of the algorithms you can use, and vice versa.
Got it. And then they jump into some of the classic data structures, trees, graphs, and tables, specifically mentioning hash tables. What makes these so foundational?
These are considered foundational because they've proven themselves to be incredibly useful and efficient for solving a huge variety of problems. Trees, for example, are great for representing hierarchical relationships, like the file system on your computer or the organizational structure of a company. And because of their structure, they allow for very efficient searching and sorting operations.
Okay, so they're good for organizing and searching data. What about graphs?
Graphs are all about relationships between things. You can use them to model social networks, transportation systems, the flow of information on the internet, pretty much anything where you have entities that are connected to each other in some way.
And hash tables. Those sound familiar, but I can't quite remember what they are.
Hash tables are a way to store data so that you can look up a specific piece of information very quickly based on a unique key. Think of a dictionary. You look up a word, the key, and it instantly gives you the definition. Hash tables use a special function called a hash function to map keys to specific locations in memory, making lookups incredibly fast.
So it's like having a direct link to the information you need.
Exactly. And that makes hash tables super useful for all sorts of applications where speed is critical, like databases, caches, and even password storage.
We already touched on access-aligned bounding boxes, or ABZs. They emphasize how useful they are for making collision detection super fast in games. Why are they so efficient?
It's because they simplify the problem. Instead of checking the exact shape of every object, you just check if their ABBs overlap. It's a very quick calculation because you're just comparing the minimum and maximum coordinates of each box. And if the boxes don't overlap, you know the objects can't possibly be colliding.
Makes sense. Then they talk about linked lists, which are made up of these individual nodes, and each node holds some data and a reference to the next node in the list. They mention that most operations take linear time, ON1, which means the time grows linearly with the size of the list, but adding or removing at the very beginning or end with a slightly modified linked list is much faster, taking constant time, O1. Why is there a difference in speed for those operations?
Great question. So in a basic linked list, if you want to find a particular item or insert something in a specific position, you have to start at the beginning and follow the chain of references, one node at a time, until you reach the right spot. So if you have a list of 100 items, in the worst case, you might have to look at all 100 items.
And that's why it takes linear time, because the time it takes grows in proportion to the length of the list.
Exactly. But if you already have a reference to the first node, and you usually do adding or removing something right at the beginning, just involves changing a couple of references. It doesn't matter how long the rest of the list is. It always takes the same amount of time. That's constant time, O1.
Got it. Now, back to recursion, that mind-bending concept where a function calls itself. They linked this to binary search trees. Can you give us another quick example of why recursion is so handy with trees?
Imagine you're searching for a file on your computer, and your file system is organized in a hierarchical way, folders within folders within folders. A recursive search function could start at the top-level folder, check if the file is there, and if not, it would call itself on each of the subfolders, and those subfolders would do the same with their own subfolders and so on. This recursive approach mirrors the hierarchical structure of the file system and breaks the problem down into smaller, identical subproblems.
So it's like automating that process of digging deeper and deeper into the folder structure.
Exactly. And it makes the code much more concise and elegant than trying to do it iteratively with loops.
Then they discuss general trees, pointing out that each point can have multiple children, unlike binary trees, which have at most two. They specifically mention quad trees and octrees, which are used for spatial partitioning. What are some situations where you might choose one of these tree structures over the others?
The choice of tree structure really depends on the specific problem you're trying to solve. Binary trees, with their simple two-way branching, are great for representing ordered data and for doing efficient searches. Quad trees are good for dividing 2D space into quadrants, which makes them useful for things like image processing and collision detection in 2D games. Octrees are the 3D equivalent. They divide 3D space into 8 octants, making them useful for organizing objects in a 3D game world or for representing volumetric data in medical imaging.
So it's all about choosing the right tool for the job. They talk about binary search trees being super efficient for adding, removing, and finding data, especially if the tree is balanced. They mention logarithmic time complexity, O log n, for those operations. But they also warn that if the tree gets unbalanced, it can slow down to linear time, ON? What's the big deal about this balance, and how do you actually keep a tree balanced?
Balance is crucial for maintaining the efficiency of a binary search tree. If the tree is perfectly balanced, every operation insert, delete, find can be done in logarithmic time.
Yeah.
But if the tree becomes skewed, like if all the nodes end up on one side, it essentially degenerates into a linked list and you lose that logarithmic performance.
So it's like having a perfectly organized library versus a library where all the books are piled up in a single room. One is much easier to search than the other.
Precisely. And to prevent this from happening, there are various algorithms, like AVL trees and red-black trees, that automatically adjust the structure of the tree as you insert or delete nodes to ensure that it remains relatively balanced.
Okay, so it's like having a self-organizing library that automatically keeps things tidy as new books come in. That's pretty neat. Then they cover the concept of tree traversal, which is about systematically visiting every node in a tree. They explain three different orders: pre-order, in-order, and post-order. What are some practical applications for these different traversal methods?
Each traversal order is useful for different tasks. Pre-order traversal, where you visit the node, then the left subtree, then the right subtree, is good for things like creating a copy of a tree or for printing out the tree in a hierarchical format. In-order traversal left subtree, node right subtree, is useful for binary search trees because it visits the nodes in their sorted order. And post-order traversal left subtree, right subtree node is often used for tasks like deleting a tree. You have to delete the children before you can delete the parent, or for evaluating mathematical expressions in postfix notation.
Okay, so the order in which you visit the nodes can have a big impact on the specific task you're trying to accomplish. Now, they introduce the concept of abstract data types, ADTs, and how they differ from concrete data types. They use the example of a list, which can be implemented using an array or a linked list. What's the significance of this distinction?
It's all about separating the concept of a data structure from its specific implementation. An ADT defines the operations you can perform on a data structure without specifying how those operations are actually implemented. So a list ADT might define operations like add an item, remove an item, get the item at a specific index, and so on. But it doesn't say whether the list should be implemented using an array or linked list or something else entirely.
So it's like having a blueprint for a house, but not specifying the materials you're going to use to build it.
Exactly. And that allows you to choose the best concrete implementation for your specific needs. An array might be better if you need fast access to elements by their index, while a linked list might be better if you're doing a lot of insertions and deletions.
So the ADT is about what you want to do, and the concrete data type is about how you actually do it.
Right on. It's a powerful concept that promotes flexibility and code reuse.
Then they move on to stacks and queues, which are fundamental ADTs. Stacks follow the LIFO principle, last in, first out, while queues follow FIFO, first in, first out. What are some everyday examples that illustrate these concepts?
Think about a stack of plates. You always add a new plate to the top, and you always take the top plate off. That's LIFO-UVO. A queue is like a line at a grocery store checkout. The first person in line gets served first, and the last person in line gets served last FIFO.
So stacks are like a pile, and queues are like a line.
Perfect. Stacks are used all the time in computer science for things like managing function calls, implementing the undo functionality in text editors, and parsing mathematical expressions. Queues are used for things like managing print jobs, handling requests on a web server, and simulating real-world scenarios where things need to be processed in the order they arrive.
They then introduce priority queues, which are queues where items are served based on their priority, not just their order of arrival. And they talk about binary heaps as an efficient way to implement these priority queues. What's so special about binary heaps for this?
Binary heaps are a really clever way to organize data so that you can quickly find and remove the item with the highest or lowest priority, while also being able to efficiently insert new items and maintain the priority order. They do this by using a special tree-like structure that guarantees that the highest priority item is always at the top.
And how are they used for priority queues?
Think of an emergency room in a hospital. Patients with the most critical conditions need to be seen first, regardless of when they arrived. A priority queue, implemented with a binary heap, would allow a hospital staff to efficiently track patients and ensure that the most urgent cases are always at the front of the line.
That's a great example. And then they tie this into Huffman coding, which, as we discussed, is a way to do lossless data compression by assigning shorter codes to more frequent symbols. Can you give us another quick, intuitive sense of how this works?
Sure. Imagine you have a text file with a lot of repetition. Maybe it's a book where certain words appear over and over again. Huffman coding analyzes the frequency of each character in the text and creates a variable length code where the most frequent characters get the shortest codes and the least frequent characters get the longest codes. This allows you to represent the same information using fewer bits overall, compressing the file without losing any data.
So it's like creating a custom shorthand system where the most common words get the shortest abbreviations.
Exactly. And the priority queue and the binary tree are used to efficiently build this coding system.
Okay, we're almost through all the core concepts. They revisit graphs and go into more depth on depth-first search, DFS, and breadth-first search, BFS, two fundamental algorithms for searching through graphs. We talked about them earlier, but In what kind of situations would you specifically choose DFS over BFS or vice versa?
It often depends on what you're trying to find and the structure of the graph. If you're just trying to see if there's any path between two nodes and you don't care about finding the shortest path, DFS might be faster because it just dives deep into the graph, exploring one branch as far as it can go before backtracking.
And BFS is better for finding the shortest path.
Right. BFS systematically explores the graph layer by layer, so it's guaranteed to find the shortest path in an unweighted graph. It's also useful for finding all the nodes that are a certain distance away from a starting node.
Got it. Then they touch on a concept they call the importance of contracts and invariants, focusing on preconditions, what must be true before code is executed, postconditions, what will be true after, and invariants, rules that must always hold true for a data structure. Why are these so helpful in software development?
Think of it like establishing clear expectations and rules for your code. Preconditions are like saying, hey, to use this function, you have to give me input in this format, and it has to meet these requirements. Postconditions are like saying, after this function runs, I guarantee that the output will be in this format and meet these requirements.
So it's like writing a contract for how your code should behave.
Exactly. And invariants are rules that must always be true for a data structure. For example, if you have a sorted list, the invariant would be that the list is always in sorted order. By defining these contracts and invariants, you make your code easier to understand, reason about, and debug.
And that makes it easier to collaborate with others too, right? Because everyone knows the rules.
Absolutely. It's a key part of writing robust and maintainable software.
Finally, they give us a taste of complexity analysis, which is about figuring out how efficient an algorithm is in terms of time and space. They mention things like O1, ON, and O log, and warn us about the dangers of exponential and factorial time complexity. Why is understanding this stuff so important for a computer scientist?
Because it allows you to predict how your code will perform as the size of the input data grows. If you have an algorithm with linear time complexity, OSN, it means that the time it takes to run will grow in direct proportion to the size of the input.
So if you double the size of the input, the algorithm will take roughly twice as long to run.
Right. But if you have an algorithm with exponential time complexity like OSA, things can get out of hand very quickly. Even a small increase in the input size can lead to a massive increase in the running time.
So it's about understanding how scalable your algorithms are.
Exactly. And choosing the right algorithm can often make the difference between a program that runs in a few seconds and a program that takes hours or even days to complete.
Wow, this CF2 course really seems to cover a ton of ground. It sounds like a challenging but incredibly rewarding journey into the fundamentals of computer science.
It is. And I think the way they blend theory with practice and the emphasis on real-world tools and applications makes it a particularly valuable learning experience.
So for you, our listener, who's looking to gain a solid understanding of this stuff, both quickly and thoroughly, this course seems like a really well-designed path. You've seen how these seemingly abstract concepts, linked lists, trees, graphs, and so on, are actually the building blocks of so much of the technology we use every day. And the emphasis on not just what these concepts are, but why they matter, is what makes this course so valuable.
Those aha moments when you see how the theory connects to real-world applications, that's where the real learning happens.
And the fact that they're teaching these concepts alongside modern industry standard tools means you'll be well equipped to actually use this knowledge to build real things.
Exactly. You'll be able to take those theoretical building blocks and turn them into working software.
That leaves us with a final thought for you, our listener. With this foundational understanding of data structures and algorithms, what new possibilities might open up for you? What amazing things might you be able to create?
It's an exciting world out there, and the tools and knowledge you gain from this course can unlock a whole universe of possibilities.
Thanks for joining us for this deep dive into CF2.